Hello, in this video we'll talk about the binomial theorem. Now the binomial theorem says that for any real numbers x and y, if we take it to the power of some number n, where n I guess is a whole number for now, we have that x plus y to the power of n, so x plus y to the power of n is equal to n choose 0, x to the power of n, y to the power of 0, plus n choose 1, x to the power of n minus 1, y to the power of 1, plus n choose 2, x to the power of n minus 2, y to the power of 2, plus, and so on, and we keep going all the way up to plus n choose n, x to the power of n minus n, which is 0, times y to the power of n. And this can be written more succinctly as the sum from k equals 0 to n of n choose k times x to the power of n minus k times y to the power of k. So we're going to show that this thing is true. Well, we're going to informally look at the idea behind it. I'm not exactly going to formally prove that it's true, but yeah, we'll get an idea of why it works. Okay, so to begin, let's start out with n equals 2. So we're going to take x plus y. We're going to take x plus y squared. So x plus y squared is of course the same as x plus y times x plus y. And we all know from year 10 algebra or something that if we expand this out, well, we're going to multiply this one by this one. We're going to multiply this one by this one. We're going to multiply this one by this one. And we're going to multiply this one by this one. So basically, we're going to end up with 4 spots because there are 2 possibilities, four different combinations. And each combination will have 2 spots, basically like this. So it's going to be 1, 2, where each of these can be an x or a y, plus 1, 2, where each of these can be an x or a y, plus 1, 2, where each of these can be an x or a y, plus 1, 2, where each of these can be an x or a y. And the reason why I knew there was 4 of them is because I know that we're going to go through all the combinations of x and y multiplied together, and given 2 spots here to put the x's and the y's, there's 2 possibilities for the first spot. It can be an x or a y, and then for each of those 2 possibilities, there's 2 possibilities for the second spot, because that can also be an x or a y. So that's a total of 2 times 2, which is 4. 1, 2, 3, 4 different combinations of the x's and y's multiplied together. Well, let's go ahead and fill them out real quick. So the first one, we got x times x, that is, well, x times x. I'm just going to write them in for now. The next one, I guess, is x times y, x times y. The next one is y times x. And the last one is y times y. So, well, if we put this together, that gives us x squared, that's the first one, plus xy plus yx plus yy. Well, xy and yx are the same thing. You know, 5 times 3 is 15, 3 times 5 is 15. Doesn't matter what order you multiply in, actually. So x times y and y times x are the same. So we can just put them together. So this is x squared plus 2 times xy plus y squared. Does that fit in with our formula? Let's check. According to our formula, it should be equal to 2 choose 0, x to the power of 2, and then y to the power of 0. 2 choose 0. I didn't actually talk about this last time, did I, in the video about permutations and combinations. 2 choose 0, we're going to define to be 1. 2 choose 0 is just 1. Anything choose 0 is 1 because it's the number of ways to pick 0 objects out of n objects, or in this case 2 objects. So 0 objects out of 2 objects, there's only one way to do that. We just don't pick anything. So 2 choose 0, and in general n choose 0 is just 1. So 2 choose 0 x squared plus, now 2 choose 1, That definitely went over, and 2 choose 1 is 2. So far I got 1, yes, 2, yes, 2 choose 1, x, y. Well, this is x to the power of 2 minus 1, which is 1, and y to the power of 1. So yes, we're correct. And I ran out of space there, but it's all good. Last term is 2 choose 2, x to the power of 2 minus 2, so x to the power of 0, which is indeed 1, and then y to the power of 2 is y squared. So yes, we got exactly what we wanted to out of this thing. So now all we got to really look at is, so let me rewrite it just because I ran out of space there. This is equal to, 2 choose 0, x to the power of 2, y to the power of 0, plus 2 choose 1, x to the power of 2 minus 1, y to the power of 1, plus 2 choose 2, x to the power of 2 minus 2, y to the power of 2. Now I want to look at where all these things come from. I want to look at where this 2 choose 1 thing comes from, and the 2 choose 2 and 2 choose 0. Well, first of all, let's give these spots labels. Let's give these places labels. So this is spot number 1. This is spot number 2. Okay, you notice we've got 2 spots here. We've got 2 spots here, and we are choosing 0 of them to put a y. We got 2 spots there, and we're choosing 0 of them to put a y. In other words, there are 2 choose 0 different ways to choose no spots out of 2 for our y to go. And so we have 2 choose 0 different ways of multiplying x together twice and y together no times. So that's where that 2 choose 0 comes from. And now this 2 choose 1 is interesting because, and these are our spots, spot number 1, spot number 2, spot number 1, spot number 2. Because both of these contribute to this 2 choose 1 term. Both these two contribute to the 2 choose 1. Why? Because we've got 2 spots available, and out of those spots we're picking one of them for the y to go. We're choosing one of them. In this case here we chose the second spot for our y to go, and in this case here we chose the first spot for our y to go. So there were 2 spots available. We chose one of them for our y to go. But because we're multiplying everything together, it doesn't matter which spot we choose the y. We're still going to end up with x to the power of 2 minus 1, because one of the spots is going to the y, times y to the power of 1. So and there are 2 choose 1 different ways to do that. The number of ways to pick one spot for our y to go out of 2. And finally, the last one, 2 choose 2. We've got 2 spots still, spot number 1 and spot number 2, and we're picking both of them for our y. And of course, there's only one way to do that, which is 2 choose 2. 2 choose 2 is equal to 2 choose 0, which is equal to 1. And x to the power of 2 minus 2, because both of our spots are going to the y. So that's x to the power of 0 times y to the power of 2. All right, let's do another example. I mean, it's basically just going to be x plus y to the power of 3. So it's not going to be like a new exciting example. Don't get too excited, but yeah. X plus y to the power of 3. So x plus y to the power of 3, that's going to be x plus y times x plus y times x plus y. How many different groupings of x's and y's multiplied together are there going to be? Well, I know there's going to be 8, because I know that I'm doing 3 multiplications here. That times that will be the first one. And then another one will be that times that, say. So there's going to be 3 multiplications, 3 things multiplied together. So 3 things multiplied together. 1, 2, 3, and each of them has to be an x or a y. So there are 2 possibilities for the first one, and then for each of those 2 possibilities, there's 2 possibilities for the second one, And then for each of those 4 possibilities for the first 2, there's another 2 possibilities for the last one. That gives a total of 2 times 2 times 2, which is 8 different combinations. So let me write them in. 1, 2, 3. 1, 2, 3. I shouldn't really be counting here. That's 1, then 2, then 3, then 4, then 5, 6, 7, 8. Oops. 8. All right, let's write them out. So first one, we multiply all 3 of the x's together. So x times x times x. Next one, let's say we multiply 2 of the x's together, x times x, and then, so we multiply these 2 together, and then we'll say we'll multiply by the y. So x times y. Oops. X times y. Now let's say we multiply x times y times x. So x times y times x, x times y times x, and then we multiply x times y times y. And that'll be the 4th one. Okay, and we can keep going. You can check that the rest will work out. So that's the first 4. Second 4, we've done all the combinations starting with x now. So let's do the one starting with y. We may as well go y times x times x. Y times x times y. Doesn't matter which order you do them in as long as you go through all of them. Y times x. And then finally y times y. Now, if we do a little observation here, you will notice that x times y and x times x and y times x, these are all the same because we're still multiplying x squared by y. Remember, order of multiplication doesn't matter. So all of these are going to result in x squared y. How many of them are there? There are 3 of them. And in fact, that's 3 choose 1. 3 choose 1. X to the, and I better write this differently actually. There are 3 choose 1, x to the power of 3 minus 1, so that's x squared, and times y to the power of 1. Now the reason for that is because we have 3 places available. We got 3 spots, 1, 2, 3, 3 places available, and we're choosing one of them for our y to go. We're choosing one of them for our y to go. It can be any one, doesn't matter which one it is, but the y has to go somewhere. And there are 3 choose 1 different ways to select one place out of 3. Notice that order doesn't matter for our selection. All we care about is that we've chosen one of the places and that we end up with one of the places chosen. So there are 3 choose 1 places, 3 choose 1 different ways to choose one spot out of 3 for our y to go. So that's how we end up with that number. I better put in the x cubed. I forgot to do that. 3 choose 0 different ways to pick to pick no y's. So there are 3 choose 0, which is 1 different ways to get the x cubed term, because there's only 3 choose 0, which is 1 different ways to choose no y's out of the 3. So that's where we are so far. Need a different color now. So notice now that x, y, y, and y, x, y, and y, y, x, these are all the same as well. These result in the term xy squared, or in other words, x to the power of 3 minus 2, because 3 minus 2 is 1, and x to the power of 1 is just x. So x to the power of 3 minus 2 times y to the power of 2. And how many of them are there? There are 3, which is the same as 3 choose 2. 3 choose 2. There are 3 choose 2 different ways to pick 2 spots out of the 3 for our y's to go. In this case, we chose the last 2 spots. In this case, we chose the first 2. And in this case, we chose the first one and the last one. So there are 3 choose 2 different ways to pick 2 spots out of 3. And 3 choose 2, if you calculate it, which is equal to 3 factorial divided by 3 minus 2 factorial, which is 1 factorial times 2 factorial. So 3 factorial divided by 1 factorial times 2 factorial. That's 3 times 2 times 1 divided by 2 times 1, basically. So that's 3. Oops, that got cut off on the bottom there. That 2 factorial. Don't worry about that anyway. If you're not sure how to calculate these 3 choose 2 or 3 choose 1 or whatever, go back and watch the video about permutations and combinations. I think I explained it pretty clearly there. And finally, we got one last one. Go back to, I'll do it in pink. One last one, y to the power of 3. In this one, we've chosen all 3 of our spots for the y terms. In this one, we've chosen all 3 of our spots. And there's only one way to do this, which is 3 choose 3. 3 choose 3 different ways to take x to the power of 3 minus 3, which is 0. And I run out of room. Y to the power of 3. I think that just fits. So x to the power of 0, y to the power of 3. There are 3 choose 3 different ways to do this because we're choosing all 3 of the spots for y's. Notice the symmetry. Notice the symmetry. It's kind of interesting because, what color should I use? I use yellow. 3 choose 0 and 3 choose 3 are equal to each other. They're both equal to 1. And that's because by choosing all 3 of them for the y's, by choosing all 3 of the spaces for the y's, it's the same as choosing no spaces for the x. And similarly, 3 choose 1 and 3 choose 2 are equal to each other because by choosing one space for the y's, it's the same as choosing, by choosing one space for the y, it's the same as choosing 2 spaces for the x. So 3 choose 1 and 3 choose 2 are the same as each other because by choosing 1 out of the 3, it's kind of the same as picking the other 2 out of the 3 in the sense that we're choosing the other 2 out of the 3 for them not to be chosen. Mull on that for a little while if it's confusing. I get it, but it sounded confusing in my head when I said it. It sounded confusing when I said it out loud. So yeah, sorry about that if that's worded badly. Okay, so I think we're ready to handle. The general case. I think we're ready to handle this thing in general. So let's take x plus y to the power of n now. X plus y to the power of n. Well, we're gonna have 2 to the power of n different clusters of x's and y's because there are 1, 2, 3. Well, ... n all the way up to n different spaces. So 1, 2, 3, all the way up to n different spaces, and each space can have either an x or a y in it, so that's 2 possibilities. So 2 possibilities for this one. For each of those 2, there's another 2 possibilities, and so on, times all the way down to times 2, and that's equal to 2 to the power of n. So there's 2 to the power of n different ways to arrange the x's and y's. Now, a lot of them are going to be the same. So I want to work out how many ways I can arrange x to the power of n minus k times y to the power of k. So x to the power of n minus k, y to the power of k. How many clusters are there that are going to give me that thing when they're all multiplied together? Well, basically, for that to be the case, I need to choose k out of these n spots. I need to choose k of them to go to y. And as discussed in the permutations and combinations video, there are n choose k different ways to do that. There are n choose k different ways to choose any k of these spots. There are n choose k different ways to pick any k out of those n spots. And once I've picked those k spots for my y's to go, well, there's going to be n minus k x's. So when we multiply everything out, it's going to be x to the power of n minus k times y to the power of k. And in general, we can do that from k equals 0. When k equals 0, it means we're choosing no y's. So when k equals 0, we're choosing no y's. And when k equals n, we're choosing all of them to be y's. So, yeah, we basically just add these things up. Because, well, yeah. You basically just add these things up because that's what we do when we expand these brackets out. We add everything together. So, in general, we're going to get the formula. The sum from k equals 0 to n of n choose k times x to the power of n minus k, y to the power of k. We've chosen k of our spots to put the y's in, and we've chosen, well, effectively we've chosen the other n minus k spots to put our x's in. And because we're multiplying everything together, and it doesn't matter about order of multiplication, that's just going to result in x to the power of n minus k times y to the power of k for each of those n choose k different arrangements here. Okay, so that is the binomial theorem for when n is a positive whole number. So yeah, everything we did here assumes n is a positive whole number. And when n is equal to, well, I guess it works for when n is equal to 0 as well. But when n is equal to 0, then it's then the whole thing is just 1, because anything to the power of 0 is 1. So let's say that n is a positive whole number. Okay, hope that was useful. Thank you very much for watching. See you guys next time. Bye.